Thank you very much, Nigel, for this introduction, and thank you, Kim-san, for the invitation and for organizing this very interesting hackathon and today the symposium. Nigel introduced me, and you've noticed that I have no specific background in philosophy or epistemology. So I take it as a privilege of invited talk to be able to talk about things you don't know. So that might be interesting for yourself as for the others. And I enjoyed looking into this. I happened to read a book last year by this Popper epistemologist, and it struck me that it was so close, what he described was so close to what we're doing now, that I should try to find a link between the two. We are currently in the midst of linked data and knowledge. When you look for linked open data, you find lots and lots of occurrences on Google. When you look for linked open knowledge, you find much, much less. And when you look for linked open data and knowledge, very often that's linked open data and knowledge acquisition or something else, which is not data and knowledge together. That is, people are interested in data and linked data, but not often realize that's part of the linked data, part of the data which is on the semantic web is more knowledge than data. And this gives background to this talk, which will cover first what's called objective knowledge in the Popperian tradition. And two things which seem important when you are in this context, which are the first relates to the question asked by Yves Lepage to Larry Hunter in the first talk about how you encode, what's the importance of encoding the trust that you have on elementary assertions. And the second is the importance of linking everything together, which in natural language processing relates to co-reference. The talk will focus on the first part and will say much less on co-reference processing. Again, some introductory comments. Text is very often used to convey knowledge, and that's why we're so interested in it in the scientific domain. And knowledge, that's more or less a quote from Popper. I say more or less a quote because I have it in French and translated it back into English because I couldn't find the original online. Knowledge becomes objective when we say what we think. So when I say something, I make it more objective than when I just think about it. And it becomes all the more objective as we write it down or print it. And maybe when we publish it in the formal representation, that is when we do what Larry described in the first talk, that makes it even more objective, as you can really see what it is and it's more formally defined. So, Karl Popper is a philosopher and epistemologist, born in Vienna, and he was both an Austrian and a British citizen. And he worked on lots of things, but the part of his work that I'm interested in today is his work on scientific discovery and how scientific knowledge grows. And this is summarized in his last book in this series, which is Objective Knowledge, an Evolutionary Approach, and the one I read is the 1999 edition. So one of the things that Popper proposed is that there are three worlds that are around us. First, the physical world, which is on the left, obviously on the drawing there. The one we live in, the one which is tangible, where things happen. And then there's what we think about it, what's in our heads. And that's the second world, the world of emotions, the world of knowledge also, but individual knowledge. That is the knowledge that we each have in our heads. And then what's proposed by Popper, which is new, is that there would be a third world, world number 3, which is the world of human productions. That is, all the theories that we build and that we share and that we can discuss. And all the problems, the problem situations, the solutions to these problems, the state of discussions of these problems, the critical discussions, the critical arguments for or against theories. And there's also in this world the information carriers, artifacts built by humans, such as books, magazines, libraries which carry information. And even artwork are included in that part of the three worlds. And what's interesting is that these three worlds are related. That is, we think about the actual world. We categorize things according to the mental classes that we have. But when we write things or say things, build things, that creates external artifacts, external things which are external to us, which may be concrete and be embodied in the first world, but which also may be just, I would say, in the air. That is, it's not embodied, such as mathematical theories or science in general. We each can think about that, but when we die, it still continues to exist. And others can think about the same thing, can discuss these things. And this world is not only what we can think about and transmit, but it also influences the first world. Because the theories that we build there, or the artifacts that we build, have transformed the world, the physical world. And even global warming was already mentioned by Popper as one of these tangible effects of our productions. So what's happening now is that there's a new citizen in World 3, which arrived with computers. Instead of writing things in books, we can write them in computer storage and make it public now through the World Wide Web, and make it more formal and better linked through the semantic web. And it struck me that this is really part of World 3. That is, this is another kind of human artifacts through which we convey knowledge, which is an kind of inscription of knowledge in a new medium. In this, when we look at computers and the way they handle knowledge until now, there's been lots of interesting things about handling knowledge which is conveyed by text, through information retrieval. The notion of hyperlinking, that is linking things together, and using this to go from one piece of information to the other, was also invented quite early. And the way using these as networks through the semantic networks and their descendants was also an early thing, and has a strong descendants. Description logics, where one way to formalize things, and all is one of the children of description logics, so that's a kind of description logics. And you notice I don't put anything after that, because I don't know any evolution after R or after description logics. That is, we are in the 80s now, from that point of view, it seems to me. And there are also repositories of knowledge, such as Medline, which went online in the 70s and public in the 90s, and Psych and then OpenPsych, and WordNet, which is very much used in natural language processing, Wikipedia that everybody contributes to, and which is a great source of knowledge also, and linking all this and providing knowledge bases online, and DBpedia, one of which is DBpedia. So that's all sorts of new knowledge repositories which are accessible through computers. Some of us have seen pub annotation, that's another one, and large corpora, annotated corpora, such as Craft. These are all artifacts that are built now, which make a large part of human knowledge now liable to being mechanically explored. So that's the age of representations of knowledge for computers and through computers. Within this knowledge, Popper tried to delineate, to define how it is that scientific knowledge grows. And for this, he assumed that, he hypothesized that there are problem descriptions from which we start, which we would like to resolve. And then we hypothesize theories or tentative theories. And most of our theories are tentative, are not definitive. And then there's a process of criticism, of study of these theories, and seeing whether they work everywhere, and trying to possibly falsify them by different kinds of tests, by critical discussion. And eventually this leads to the identification of new problems identified through this critical discussion, which become new sources of investigation, and we loop, or rather spiral, up and up to new knowledge. In general, there are multiple tentative theories, and they are compared and criticized, and we like to select the best. That is, the one which fails less, or the one which has more pragmatic value. So this is the general scheme. And when you want to prove that something is true, you can use deduction. This is, for instance, a tentative theory, and it has a consequence here. And you know that the contrapositive is that if the consequence is false, then the theory should be false. So in one direction, you from the theory to the conclusions, you transmit truth. And this is what's used mostly, what mathematics and other demonstrative sciences like to do. That is to prove new things, which and some theorems can be proven true, and then definitely be true. Whereas in experimental sciences, in empirical sciences, it's difficult to find any theory which you're certain that is fully true. So, in general, logic, in that case, it uses a contrapositive and is used to retransmit falsity. And that's refutation. So, refutation shows that a theory is false, or at least that it has some drawbacks, it's not perfect. And this is, again, done through the critical discussion of all the parts of the pieces and bits and pieces of the theory and its implications. Sometimes that's not the theory itself which is false. That's the way you try to derive a consequence. And then that is, each of these derivations uses possibly auxiliary theories. So for instance, when you measure the temperature of something, you use an instrument. And if the instrument is the wrong one or doesn't work, then that's not the theory which is wrong, but the way you perform the experiments. So each step in the construction of a theory must be subjected to this critical discussion process. Well, what are scientific theories? At our level, and what we've seen mostly in the current discussions, is facts and statements, for a large part in our domain, extracted from text. So you can directly substitute for this Larry's slide with the full analysis of a sentence, but I didn't have that, so I took what I had. And that's French, but you see more formal representations above them. So that's mostly what we'll have as elementary pieces in our representation of how we think the world works. You can have, of course, more complex statements, and that's more like what Larry showed, except that this is at the level of several documents, or another one here, and this is a concentrated representation of the same thing, or implications and things like that. So these are the theories that we are currently discussing, several facts and statements and their interrelations. In the previous slide, I discussed the importance of being able to discuss the truth of things, or to falsify, to criticize things. So that's when we have this schema, we should be able to discuss the correction or falsity of things. We need to record the whole chain of reasoning that led to a given theory. That is to record each fact and statement and claim and hypothesis and so on. And we must record the status of each fact, that is how it was derived, or whether we really believe in it, and to which level we're certain of it. And if there are competing hypotheses, we must also record them all and assert that they are competing. And we must do this both at the level of written text, or the basic level at which we find generally this information, and also on formal representations, and link all that together. So what I tried to do was find out how this was dealt with in current representations. And I tried also to link Popper's name to some current work, and it was very hard. I identified one work which is called the Semantic Web Applications in Neuromedicine, the SWAN Ontology, by Paulo Siqueiros and colleagues. And in this ontology, which was designed to describe scientific discourse, there are discourse relationships which enable you to say that something is a claim, a hypothesis, and other things. There's also, of course, lots of things which exist elsewhere, such as agents, the authors, and other individuals, and their relations. The notion of provenance, which enables you to track at least one level of ancestry of a given data, and qualifiers, which is meant for the contents of these things. So the basis is these building blocks in the ontology, with the qualifiers and the provenance and the discourse relationships. And then it's complemented by more specific things when you want to have more specifically scientific discourse, with the notion of citation and the claims and so on. And then they use it more specifically in Alzheimer's disease, in work on Alzheimer's disease, with more specific things and more specific sub-ontologies for this domain. And this is an example of a claim in SWAN, using the SWAN ontology, where you have here the piece of text, which is either the title and then the description of the claim which is made, and what supports it. So that's the backing of the claim, and then other part pieces which I want to detail more. And here is a graphical representation of this, where you have centrally the claim and the text it's attached to, and then the different supports that it has. Yes, supporting evidence on the left. So this is very nice, and you see it links also to a text, although it cannot link to the portion of the text that was not the intent. Yes, so it cites a whole publication, but rather than fragments. There's only elementary links, and it doesn't care for whole networks. And it was actually reused in the Open Annotation Ontology, which is a more extensive description of this kind of statements. And the Open Annotation Ontology, among many other things, adds provision for document fragments. By the way, the sharp 5 here refers to the first slide in this chapter, in this section, which is so it does this in links to text, and when it's 3, it links to the status of things and so on. So gradually we have different pieces of the requirements which are fulfilled by these methods. So here is an example of the curation statement in the Open Annotation Ontology, where you have here the piece of text and here the statement, the claim, and there you have the notion of curation, where it says somewhere that this is accepted by the curator. So this is validated, and we have some trust in this piece of knowledge. Then CNRS and colleagues, Clark here, criticized part of this and compared different ways of representing these scientific statements. And more specifically, they were interested in being able to represent arguments and evidence, supporting evidence. And what they compared this to ontology, also the biomedical element language, is that correct? And
biological expression language. Biological
expression language, thank you. Fabio will be talking about that. And notice that none of them support claim networks of claim, and the direct empirical evidence, which supports that also. And they proposed the notion of macro-publication, which covers these needs, and that covers more needs, more of the requirements that I set out in this Popperian view. So they can represent a principal claim and the statements which provide evidence to support this claim or to challenge it. And so this is a first-class citizen in their ontology, and all these are combined into this notion of micro-publication. So here is an example from the paper about micro-publications, where you have here an argument, let's say, which says that this is, so you have here a series of supporting previous knowledge, and this is a criticism of a piece of knowledge here, which is challenged by this fact. So you have both supports and challenges relations. So this paper by Patricia Spearman supports this claim and somewhat reviewed the literature and said, well, all these previous publications, all these previous facts or claims or hypotheses support that fact which challenges this one. So that's a way to represent explicitly a scientific controversy, an argument with supports in one direction and supports in the other direction. So that's actually happening here, the notion of critical discussion that Popper advocated, that Popper described as being the basics of science. And now it's starting to be represented explicitly in a network of supports and challenges. Once you do that, there's plenty of literature, there's plenty of background to work with it. And managing argumentation has a long AI tradition. And there's a recent review about how to manage argumentation by Schneider and colleagues, which reviewed more than 150 research papers on the topic and found out 14 semantic web models for argumentation, 37 tools which implement that on the web. So this closes the section I wanted to present about this notion of arguments and criticism, and I'd like now to move to co-reference. So co-reference deals with the fact that two mentions of the same entity, well, two mentions typically in a text refer to the same entity in the world. You can sometimes paste together or glue together two different things in there. One is what I called here closed co-reference, where you know in advance the whole set of entities that you might link to, and you would like to know which entity among these is referred to in a piece of text or in a piece of knowledge. And the other one, which I call open, but is a situation where you have references to something, but you don't know exactly what this something is, and you just want to know that two mentions in the text typically refer to the same thing, but you don't know the name of this thing in the text. So, for instance, for normalization, that is the second part, here is an example, maybe not so readable, where you have two instances of two mentions of text here, which are anatomical part, which are more specifically concepts, 24.109, and again here, 24.10 and the 9 is just behind here, which is lung. And these two pieces of text refer to lung, to this lung concept. So they both relate to the same entity in the world. And co-reference in text, which part of which is called anaphora, has two mentions in the same text. For instance, here this strain and the name of this bacteria, and the second one refers to the first. So we don't know, here we don't necessarily know in advance what's the set of entities that we have. We just identify them, or identify references to entities as we go through the text. And at some point notice that two of them refer to the same thing. So what I wanted to stress here is that without co-reference, there's no linking, obviously, but this, without co-reference, you would not be able to link sentences together. That is, you would have, for instance, in a scientific paper, you would have just a set of sentences and with a set of representations, and that would bring you not much further. You would not be able to aggregate this information and to share it with something else, because it would still remain in an individual. When you have different scientific papers, they would have each of them would have its representation, which would be disconnected from the rest if you're not able to identify the fact that they refer to the same things. And that's even true for people. If you were not able now to understand what I refer to when I'm talking, I would be saying things and you would be hearing things, but not necessarily the same, and there would be no communication. And science would record nothing, and each new individual who's born would learn everything from scratch and have no background knowledge, which would be transmitted by being able to say that this and that are the same thing, and that I can take advantage of this to reuse former knowledge. A simple example of the impacts in text processing of co-reference. That's one of the tasks in the Biomedical task in 2013 and also in 2011 was called bacteria biotope. The task, one of the subtasks was to detect relations between bacteria and their locations, their biotope where they live. And when in this, with the corpus that was given, when you don't process co-reference, when you don't solve co-reference, you find a drop of 13 points of F measure. That's what they found here, and we found 7 points. So maybe our co-reference resolution system was less good, or our relation system was better, but anyway, that's a huge drop anyway. So for instance, here in the example that I showed in the previous slide, if you're not able to know that this bacteria is mentioned again here through this strain, you will miss the relation which is explicit in this sentence. This strain in the extraintestinal mouse is not viral there, but it is there. And this should be linked to the fact that this bacteria, which is named here, has this relation, this location relation with these two habitats. The rest of this section is just mentions a few questions around co-reference resolution. If we do perfect co-reference, that means that we're interested in specific entities, biomedical entities. For instance, as in the previous slide, we want to find which one co-refer to one another, to aggregate the properties that we collect as we have more facts about them. Same for biomedical events, where we collect more and more knowledge about a given type of events. Well, we're interested in tracking publications, for instance, to be able to cite publications, to build citation networks. We want to track authors, and that's not so easy, because some people have names which are, for instance, Kim is quite common. Zweigenbaum is less common, but still there are at least 2 in that line. And statements, of course, is the most important to build theories. So we want to track statements so that we can identify whether we're talking about the same piece of knowledge or whether we share the same interest, and of course also the status of this statement, so that we know whether we should trust it or whether it's negated or suggested only. Larry talked about generic readings of entities, which is the most common in scientific papers. So there's a difference between liver here as general, which produces bile, and then when I say my liver is swelling, that's not liver in general, but that's a specific instance of liver which has this. So the second is generally not present in the literature, but when you work on texts from hospitals, that's the reverse. This one is more common, and the first one less common. You find co-reference at different distance. That is, sometimes you find 2 mentions of an entity in the same sentence, sometimes in 2 different sentences. That was the example that I gave. And then a very interesting kind of co-reference occurs across different documents, which have maybe been written by different people, and that's where knowledge aggregation operates. And sometimes also even across different types of documents. So, for instance, in the scientific literature, you have citations from one document to one paper to the other, but this also happens, for instance, from patents to the literature, and there are different genres of documents. And it's important to be able to record the context of a citation and its target, and that's, for instance, what was done in the last year's biomedical summarization track at TAC, where the notion of a citance, how a document, how another article is cited, is very important. So this is a part of the building the context and building the different types of support, or on the contrary, challenges information from the way documents are cited. And another part of the problem is, or another part of the activity around this cross-document linking, the cross-document co-reference, is being able to see that 2 documents mention the same statements. And that's what the people in the open annotation do also, and they call it similogs. So here you have a series of sentences, and actually here claims or hypotheses obtained from different publications. And the challenge is to identify that each of these says more or less the same. So rapamycin potently inhibits downstream signaling from the target of rapamycin or proteins, and you have more or less the same, not necessarily the same words, not necessarily the same expressions. So that's more or less paraphrases, and these are called what I would call co-reference, or event co-reference, or closed level co-reference, is here called similogs. And there's one of them is taken as the representative of the class, and this one is called the holotype of the series. So it's a very interesting challenge to be able to recognize, to detect co-reference at that level. So with this, I'll close the sections that I wanted to cover, and conclude about first the fact that it seems that what Karl Popper described as the World 3 of human artifacts as objective knowledge the part of which was inscribed in books and libraries is now inscribed in computers, and the web and the semantic web make this even more explicit. The semantic web gradually exposes more machine-readable objective knowledge, objective because it's explicitly stated and can be discussed. And you've seen that it's more and more explicitly exposed to machine, well, at least to machine traversal, to exploration through computers. It crucially depends on coreference, because that's the basis of linking and aggregation. And only recently has this notion of critical discussion, which is so important in science, started to be addressed by these representations. It's been around all the time, of course, and it's been around especially in the artificial intelligence tradition with trying to manage arguments and counter-arguments and the rest. But it seems only recently to have been encoded in this area of representing the contents of scientific documents, scientific publications. So I've outlined three possible conclusions, final conclusions of this, which is one is that this opens a new phase of machine-assisted scientific discovery. That's probably the most correct thing to infer from that. If you're more confident in what machines can do, you could say that this paves the way for machine discovery of objective knowledge. That is, now that we have exposed more precisely all these bits and pieces of knowledge, we can maybe run automatic systems, just the way the people have done already to do literature-based discovery at the level of Medline and abstracts. Do it more precisely on the precise facts that are discussed there. And let machines do that, let programs do that. Or maybe this is just another step towards a World 3 for machines, and when machines have that, they'll be as smart as we are, and we'll be in another world again. Thank you very much.